Hello, this is Mr. Ferris. I'm here to go over the College Board practice problem with you. I found some issues that we need to discuss, I believe. So start out with the table that you were given between the genetically modified corn and the regular corn, and they even put the differences statistics in there. And you had a box plot given of the difference in yields. One of the questions they asked you to do is to describe the distribution of differences. So you were supposed to describe it based off of the graph, and then they also, of course, gave you the statistics that you could use if you needed to. So once again, one of the basic things that likely will come up somewhere is the ability to describe a distribution. And these principles would also apply to when you're comparing distributions. The exception would be you would have to add comparative language like greater than, less than, more skewed, less skewed. But generally, there's 5 things you always want to put in a description of a distribution. And that would be shape, center spread, outliers, and context. Now we know, hopefully, that box plots cannot give full descriptions of shape. Although in this case, you can see there's an outlier clearly to the right, and it looks like the bar coming out from the third quartile is longer here than the bar coming out from the first quartile there. So you put that together, and you could suggest skewness, and maybe I would say it like that. It suggests skewness to the right. But you cannot tell modality, you cannot tell normality, you cannot tell about gaps or clusters. But you still can talk about the median, you can talk about the IQR or the range. And you might want to remember too that because a skewed right distribution is seemingly suggested here, we probably should stay away from the mean and the standard deviation. Those are more for at least symmetric or kind of normal-like distributions. Also, I've noticed that some of you are stating that range is between 2 numbers, and that's really not true. A range is a distance. An IQR is a distance. There should be a single number attributed to the range, in this case 22.2, or for the IQR, which is 6.9. Ranges and IQRs are distances. They are numbers. They are not a range between 2 things. And just a little question about why do we want to use median and IQR when data is skewed? Well, that's because they're resistant. Medians and IQRs tend to be more resistant to either skewed right, skewed left, outliers in distributions. And just an aside, speaking of distributions, this is the distribution of the scores for this problem. Since there were 5 parts, I graded every part on a 2-point scale. Like 2 would be essentially correct, 1 is partially correct, incorrect is 0. And so that would give you 2 points per part, and there was one person that got all 5 parts correct. So in my mind, if I were the king of AP grading, I would probably say that anybody that got an 8 or higher on that problem probably would deserve a 5 on the AP exam. Those that got 6s and 7s, in my mind, probably earned a 4 on the exam. And those that got 4s or 5s probably earned a 3. Now, 3 or higher on an AP exam is considered passing. We, of course, like to shoot for 4s and 5s because 4s and 5s tend to earn college credit. So that's the distribution of this particular problem. Also, one of the problems on the practice problem talked about independence. Are these 2 varieties of corn independent based on the way that they were put in the plots? So we really need to go back to the definition. In your textbook, this is in the probability chapters, 2 events are independent if knowing that one thing has happened doesn't change the probability of the other thing happening. So in this case, it's the 2 yields, and because they put genetically modified in one half and regular in the other half, of course they did it by randomization, so sometimes you have it other ways. But every plot was divided in half, and some of you were commenting on, well, if you knew where one went, you would automatically know where the other one went. But that's not really what we're investigating. We're investigating the yields. So really you have to ask yourself, if knowing that, let's say, corn A did better in plot 1, is that going to give you any information of how the other variety did? Well, when you think about things like, there might be trees on one side, there might be a lake on one side, there could be a farm along one side. So let's just say plot 1 here, for some reason, is just a really rich plot. Well, if A does really well in there, then it's pretty likely B is going to do well as well. So knowing that A did well does seem to give you an idea how B might have done. And so these are not going to be independent. You could also make an argument that if this is corn and A is planted right next to B, well, their roots are going to be affecting each other. You could even go from that angle, that the corn will literally be affecting each other's yields because they're so close together. Now, of course, in real life, I suppose you could put a gap in between there so that doesn't happen. But you can make up some scenarios where you can give a good reason why these are not independent. And the same thing for a plot that's maybe bad. Maybe the plots next to this farm are going to be worse in general. Well, if it's going to be worse for B, it's probably going to be worse for A as well because they are in such close proximity. So that was the argument you want to use. You want to make sure you know what independence is. That's a very important concept in statistics. And then there was a question about which of the two types of corn would be more likely to yield 123 or more. I'll tell you what, I struggled with this. I was thinking it one way, and then I changed it, and then I wrote the other answer, and then I changed it back, and then I changed it back. I can't remember how many times I changed my answer. It wasn't until I graphed it, and I just sketched it. I didn't do a fancy one like this for you, but I just sketched it, and finally, when I sketched it, and I put the 123 on there, kind of like a red line, medians are the statistic that tells you where 50% of the data is. You really should argue everything on this question about the medians. And so when we draw a little fancier graph like I did, it should be clear that at least 50% of the data in the genetically modified group is above the red line, above the 123. Whereas in the regular, and again, you have to say that in your explanation, whereas in the regular distribution, you have, it appears to be less than 50%. I guess we don't know for sure it's less than 50%, but it's certainly not more than 50%. Or you could even argue from the other side, it looks like at least 50% is going to be below 123, and it's pretty likely that maybe more than 50% is going to be less than 123. You want to argue from the medians because medians tell you where 50% of the data is. Means do not. Means are affected by skewness and other things, so means don't guarantee you have a 50-50 split. And just another note here, we have a box plot that looks very symmetric, looks very perfect. And some people might say, hey, that looks pretty normal. Well, it turns out, if you peel away and look at the dot plot for that, it's not close to normal. There's a huge gap. Well, there's several gaps, and it's bimodal, and there's like 74% within one standard deviation, not 68%. So there's a lot of problems with that assumption that just because a box plot is very symmetric, that does not tell you anything about normality. So some of you did some normal calculations on that problem, and that is just not appropriate for that one. All right, we're still having trouble interpreting the large counts condition. You may remember we'd like to have 30 in our sample size for means when we're doing mean inference procedures. Why is that? Many of you wrote down it's so you can use a normal model. And that is partially correct. But a normal model for what exactly? What do we want to be normal so that we can do our inference procedures correctly? Well, let's go back to a demonstration that you might remember. This was supposed to be modeling, I think, the ages of pennies in the population. So the population's probably skewed right. Most pennies are young in circulation, but there's a few that are maybe old. So what we want to do is think about, okay, if we're sampling, and we're taking samples of 5, remember what that is, 1, 2, 3, 4, 5. Oh, actually I've got 25. So we're doing a sample size of 25, and a sampling distribution is built by taking numerous samples. So far, I've got one sample mean, one X bar sitting here from a sample of 25 from a population that I guess we could even assume is maybe close to infinite. So don't forget there's 3 distributions that we talk about a lot in statistics. There's the population distribution. This here is a distribution of one sample of 25 pennies. And then this is the beginnings of a sampling distribution that will pile up if we continue to sample. Now, in real life, a statistician just gets this. This is all they get. They do one sample one time, and this is what they get. But what they have to remember is, well, what if? What if we did many, 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 many more of these? So let me back this up to 5, just to show you. If we did many, 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 many samples of size 5, the sampling distribution is, kind of normalish, but you can still see there's a tail to the right, and that's still from the kind of the parent population. But if we bump this up to 25 and do lots and lots and lots of samples, you see it's way more normal. So the reason we like our sample size to be close to 30 is because when you start getting close to 30 in your sample size, then the sampling distribution becomes approximately normal. And that then opens the door to doing T procedures like intervals and tests. One thing I can show you too through the magic of Desmos, the red is a normal distribution. The blue is a T distribution. And right now, that's a sample size of 3. So if you did a sampling distribution for a sample size of 3, and you did sample means, this is what the difference would be. So there's a pretty big difference between a T distribution and a normal distribution. And you would not want to use a normal distribution for this because this is the way, the blue one is the way the data is really, or the sample means are actually piling up. But let me change the degrees of freedom and consequently the sample size to bigger and bigger sample sizes. You can tell it's getting closer and closer to normal. In fact, at some point, you can't tell the difference between normal and T. So where does this happen? Where would you say, well, that's close enough, we'll just call it normal? Somewhere in here, you would say, well, that's close enough, we'll just call it normal. Well, statisticians have kind of landed on this. Right here is where they believe that a T and a normal are close enough that you could just say it's the same. And this is when N is 30. When you have a sample size of 30, that's enough to say, okay, our sampling distribution is approximately normal, because look at this. I mean, there's hardly any difference between these. But of course, it's still not exactly normal. So that's why a t-table comes in. And so what you might remember is the t-table, these numbers change in here, and the very bottom row on a t-table where it says infinity is technically a normal distribution then. So a t-distribution, when you have an infinite sample size, would actually be a normal distribution. It's kind of a math theory thing. But look up here where normal was. When we said that a sample size of 30 was close enough to say that this is approximately normal, this is what we're saying. We're saying, well, really, it's a t with the degrees of freedom of 29, and that's when we say that's close enough to normal, or we say it's approximately normal. Now, the truth is, it's really not. It's still a t distribution. Even when it's 40 or 50 or 60 or even 1,000, it's still technically a t distribution. But a t distribution up in this neck of the woods is essentially an approximately normal distribution. So the full answer on that problem would be that yes, we can assume a normal distribution, but that then just opens up the possibility to do a t confidence interval or a t test. And so that's the way we would want to talk on this. The full best answer on this, why do we like a sample size greater than 30? It's so that we can assume a normal model or an approximately normal model distribution for the sampling distribution of X bar, which in turn then allows us to use t intervals and t tests. That's kind of the full answer. So I hope that was helpful. That was a quick run through of some of the loose ends that we still need to get better at. But fortunately, we've still got time. So let me know if you have any questions along the way, and I'll see you in class.